Okay, so here, let's get into this. We're going to talk about the first law of thermodynamics on this one. There are several laws of thermodynamics. In Gen Chem 1, we talk about the first law. Um, we're going to get this under control here. Um, energy, this is kind of the official phrasing, I suppose. Energy cannot be created nor destroyed. It only changes form. We can think of it as the total energy of the universe is constant. Um, right? This also means when we're doing a chemical reaction, the total energy involved isn't going to change. Okay, so we talk a lot about energy and how we're switching some stuff around as we do it. Okay. When we think about energy, really, we're thinking about there's two. Ooh, shoot. I don't know why that happened. Okay. Two kinds, big subcategories of energy. Potential energy is energy that is due to the structure of a substance or the state of a substance, right? This is our chemical energy, right? This also deals with position, right? So gravity is potential energy, right? This person is smushing the spring together, and so they're storing energy in the spring. When they let it go, it releases all that energy, right? From a chemistry standpoint, a lot of the energy is stored in bonds, okay? Meaning that, you know, bonds have a particular energy associated with them, right? We've talked about bond dissociating before, right? Strong bonds, weak bonds, bond order, bond length, all that stuff. But everything's also constantly moving. And so bonds are vibrating, so they're stretching in different ways. They're bending, they're translating a little bit, they're moving around, they're spinning, they're rotating, they're doing all this stuff. And that's all ways that molecules store energy. Okay. Um, the other big kind that we're thinking of here, maybe not, I don't know. There we go. Is kinetic energy. Kinetic energy is due to motion. So anything that's moving will have kinetic energy. So that's not a good option. Um, anything that's moving will have kinetic energy. And so again, the total energy of the universe is constant, but what we're doing if we're thinking about this from a physics point of view is that we're converting potential energy into kinetic energy. And so here, when the ball is at the top, it has potential energy because it can fall down. As it's moving, it's converting that potential energy into kinetic energy. Okay. As it's moving back up, it's converting that kinetic energy into potential again and storing it back in here by getting, excuse me, higher up. It's the same process in a roller coaster, right? The roller coaster doesn't have a motor. It's not driven on the coaster. It is dragged up to the top, and then gravity pulls it down, and kinetic energy is transferred into potential energy, right? This guy in the the archer here is pulling the bow back, putting potential energy into the system by tensing up the bow and tensing the string, and it converts it into kinetic energy when he lets it go. Okay. One thing to think about here is because since molecules are constantly moving, motion and heat is kinetic energy, right? Because things are moving, that's kinetic energy. So this is going to relate when we're thinking about stuff. Okay. Ultimately, what we're going to be concerned about is something called internal energy. And excuse me, internal energy is the sum of all the kinetic energy and all the potential energy of all particles in a substance. Okay. So whatever that thing is, right? It's made of particles. It's sitting in a gravitational field, right? Is it high up? Is it low down? Is it at sea level? Is it on a mountaintop? The bonds are made of particular things or particular atoms. Your protons, neutrons, electrons are all sitting there vibrating. They're moving around in orbits, right? They're doing all this stuff. And that, even though it's just sitting there, stuff is happening and things are moving, right? It has a measurable temperature. So there is heat involved and there is internal energy. Um, unfortunately, we cannot measure, oops, let me go back. We cannot measure internal energy directly, but that's okay. What we can do is we can measure changes in the internal energy. And this is what's going to be more important for us, is to look at the changes in energy. Okay, so internal energy can be a lot of things. This is a nice graphic I found. Translational energy is energy of moving, right? You're going, like, say your atom is over here, and now it's over here. It's spent kinetic energy to move over there. Everything has translational energy. Okay, a monatomic gas, this is like, say, neon, a single atom. Okay, molecular gas is a molecule, so it's also going to have vibrations, it's going to have rotations and their kinetic energy. Okay, and all the bond stuff. And then if you're a condensed phase in a liquid or a solid, you also have intermolecular forces. So intermolecular forces are another big set here. Okay, our internal energy is given the symbol U. Okay, and when we're thinking about changes in internal energy, we can say delta U. Okay, we're also going to be able to say this because internal energy is a state function, right? So we'll also be able to say that delta U should be equal to U final minus U initial, which is going to be good for us for being able to figure out, maybe I'll go back. That's going to be good for us to be able to figure out what's happening in reactions as we're doing stuff, okay? So let's look at a reaction. Let's take sulfur as a gas, react it with oxygen gas, and get sulfur dioxide as a gas, okay? And if we want to think about it, our delta U, right, this would be the energy for 1 mole of SO2 gas is going to be, oops, all right, this is our final is products, and initial is reactants. So our delta U is final minus initial. So energy for 1 mole of O2 plus 1 mole of S2. Okay. And so we can use this guy to figure out what's going on. Oftentimes what we're doing is we're just measuring the difference, right? We can do the reaction and say, okay, this is what it was before, this is what it is afterwards. And we can say, okay, in this example, this reaction gives off or emits 296.4 kilojoules of energy. Okay. So what, ooh, crap, let me go back. So what this means is our delta U then is negative 296.4 kilojoules. So this dude is exothermic because heat is coming out. This also means the internal energy of the products is less than the internal energy of the reactants. Okay. All right. What this means, though, is if our reaction is giving off energy, it's exothermic, that means all of that energy has to be going somewhere, and it's going into the surroundings. Okay, so this brings us to first law. Okay, right. Okay, first law, remember, is telling us that the total energy is constant. We're only changing that. You can't read that. Right? We're only changing the form of the energy. Okay. And so anything that changes the internal energy of our system will also change the internal energy of the surroundings. And this is going to give us the change in energy of the universe. But the change in energy of the universe has to be zero. This is what's demanded by the first law, right? Okay. So what this means is, let me write this again. Our delta U of the system plus the delta U of the surroundings has to equal 0. So anything that happens in the surrounding, in the system, sorry, is equal and opposite of what happens in the surroundings. Okay, so if the system is giving off energy, it's going into the surroundings, and the amount of energy that's doing that is the same. So in our sulfur example, this means that if our system is giving off 296.4 kilojoules, that means the surroundings has to be gaining 296.4 kilojoules. Okay, they're equal and they're opposite. Okay. All right, so we got to think about now, how are the system and the surroundings exchanging energy, right? We said this in the beginning. There are two ways that energy can be exchanged. They can be exchanged through heat, and they can be exchanged through work. Work is W, and heat is Q. Okay, so system and surroundings can exchange heat, right? If the heat comes out of the system, it goes into the surroundings. If the system takes in, we always reference the system. So if the system takes in heat, it's taking it from the surroundings. We can say the system did work on the surroundings, or the surroundings did work on the system. And so we have work there as well. Okay. Because of this relationship, we can say that the delta U is equal to any heat that was exchanged plus any work that was exchanged, right? So our delta U is going to be Q plus W, okay? We just have to watch out for the sign of the thing, okay? Right, then again, delta U is Q plus W, okay? But we just have to watch out for, is the heat or the work going into or out of the system? Okay, because heat or work could be positive or negative. And just remember that positive is into the system and negative is out of the system. Okay, so that's what we're dealing with here. We're looking at, is the heat or work going into or out of the system? Okay, so we have to think about what's going on as we do that. Let's look at some examples here. Okay, here in our first one, we have steam condensing, right? So what we're having here is we're having gaseous steam turn into a liquid, okay? Is this an act of work, or is this an act of heat? This is an act of heat. And is that heat going into or out of the system? Well, the gas is higher energy, the liquid is lower energy. So this is coming out. This is heat out. So heat out means this is a negative value of Q. Okay. If we have ice melting, this is ice that's a solid turning into a liquid. Okay, again, this is a question of heat. Okay, because the ice is melting, we're going from solid to liquid, we're going from a low energy state to our higher energy state. We have to put energy in. So heat is going into the ice to melt it. So this is a positive value of Q. Okay. Lastly, we got this guy who is moving a fridge. Okay. He's pushing the fridge. If we think of the fridge being the system, okay, so fridge is the system. Okay. What's happening? This is a question of work because he is moving the system, right? He's doing a force through a distance, so that's work. Okay. Since the system is being worked upon, we are saying work is being done on the system, then this is a positive work. Okay. Work is a little bit harder to see, but we can work our way through it. All right, let's work an actual example. I'm saying work too much, but let's do an example here of what we're talking about. Okay, so a system releases 1587 kilojoules of heat and 479 kilojoules of work are done on the system. What is the change of internal energy for the system? So this is delta U is Q plus W. This equation will be given to you, so there's no need to stress about it. What we have to think about is whether or not things are positive or negative. So let's figure that out first. Heat is Q, okay? Our Q is 1587 kilojoules, okay? We said it released it, so that's heat out, so that's negative, okay? Our work then is 479 kilojoules, okay? And this is done on the system, which means the work is positive, okay? The units are the same, kilojoules and kilojoules. So we don't have to convert anything. We just have to plug and chug as we go. Don't know why sometimes this is just being weird today. Okay, so let's do that. Delta U is equal to Q plus W. Our Q is negative 1587 kilojoules, and we're going to add to that 479 kilojoules. Okay, let's do that. You can think of it as the same thing. I'm doing my calculator this way, saying 479 kilojoules minus 1587 kilojoules. It's the same idea. This is negative 1108 kilojoules. And that's the right number of significant figures because both of these have 0 decimal places. I didn't ask for a particular unit, so we can leave this in kilojoules. That's our delta U. Okay, so overall, energy is leaving the system and going into the surroundings. Okay, if you have any questions, let me know. We're going to get some practice on this as we do it. The big thing with this is figuring out if the heat or the work is positive or negative. That is the crucial step. Okay, and then only convert units if you need to. Okay, all right, I'll catch you later. Let me know if you have problems or questions, and I'll see you in class.